Again, it has N input, 2 to the N output, and chip enable. Sometimes you have more than one chip enabled. You could have 2 or 3, 4 enabled. You'll see in the lab, it says for this chip to be on, you need this pin to be high, this one to be low, and that to be high. Or it could be 2 of them. So for example, a 2x4 decoder will look like this. It has 2 inputs. This is a 2x4 decoder. It will have 2 inputs and it will have 4 outputs. And the way this, and a chip enable, and the way this one works, EN for enable. The way this one works, we'll say A and B. This is output 0, 1, 2, 3. If you want to look at the truth table for it, assuming the chip is on, I'm not going to put what the enable is because that depends on the circuit itself. Here's A and there's B. If they're both 0, that says output 0, we have output 0, output 1, output 2, output 3. Only one of these guys will be on at any given time. Only one. So when the inputs are 0, 0, it says this one, 0, will be on. So this will be on and these guys will be 0. 0, 1. That's a 1. Only output 1 will be on, the other 3 will be 0. 1, 0. Only output 2 is going to be on and the other ones have to be 0. When this is 1, 1, that's a 3. The first 3 will be off and the last one will be on. Assuming the chip enable is on. The way I drew mine here. Assuming the chip enable is on. EN is 1. So if this is on, that's how it works. If this is 0, the enable is 0, nothing will happen. The output's always going to be 0 regardless what these are. It doesn't matter. It doesn't matter if this is 0, 0. If this is 0, 1, nothing will, you will not get a 1. 1, 0, still all zeros. 1, 1, still all zeros. So if the enable is off, you're not going to see anything. So the first thing you have to make sure is that chip enable goes on for it to work. And why is it only one of them on? Why one of them on? Well, let me show you what the inside might look like for a 2x4 decoder. We say we have 2 inputs, 4 outputs. Anyone still writing there? What does the inside might look like for a 2x4? If we take that and dissect the 2x4, I'll make the box bigger. This is what a 2x4 looks like. That little box that you saw there, I'm going to make it much bigger now. We say we have a chip enable right here. And let's make the enable, let's run the line through this like a wire now going through the whole thing. We have 2 inputs, we said A and B, right? This is A. This is B. So let's stretch them through. This is B now. And this is A. So this is really A, B, and enable. We got these wires going through it. So this is output 0. This is output 1. This is output 2. And this is output 3. Each one of these is an AND gate. That's what the inside of each one looks like. So for the first one, you want it to be on, you want it to be high, and these guys low. Well, when you want that to be on when you have 0, 0, 0. If you look at that truth table, when these guys are 0 and the enable is 1, you want it to be on. So what I'm going to do, I need to make sure this has a value of 1. So I'm going to attach the enable to this. I'm going to attach A and B to it, but since A and B have values of 0, nope, I didn't mean to go that far. This is a NOT gate. This is a NOT gate here. And notice what happens when you have a 1, 0, 0. When the enable is 1, A is 0, and B is 0, what's 1, 0, and 0? You come to this end, what do you have? 1, 1, 1. What's the value of that? 1. So this guy will have a value of 1 when the enable is on, A is 0, and B is 0. This one, you'll have a value of 1. Here's the chip enable. Has to be on. Now you want A to be 0 and B to be 1. A to be 1, A to be 0, and B is 1. Yep, I said it correct. So this is B is 1, and you want that A is 0. So I need a NOT gate there. Notice you have a 1, 1, 0. Chip enable is 1. A is 0, B is 1. A is 0, B is 1. You want this one to be on. Well, what happens when A is 0 and B is 1? We know there's going to be a 0. That's out. What about this one? You'll have a 1, 1, 1, and you have a value of 1. This will be a 0. Once one of these guys is 1 here, when you complement that, you end up with a 0. The result is 0. So when you put in 1, 1, 0, this is off, this is on. The next one, you want that to be on when it's 1, 1, 0. The chip enable is 1. You want A to be, B to be 0 here. Oh. So I got to put a NOT gate there for B. And I want A to be 1. Notice I put 1, 0, 1. I put, that's the chip enable 1. And I put 1, 0. That's why I did A is 1, B is 0. A is 1, B is 0. You're going to have 1, 1, 1. You'll have a 1 here. this will, if I put 1, 0, 1, this will be a 0, gone. This will be a 0. Notice once you put a 1 here, once this is 1, what's the value? 0. This is off. What's the value of this? 0. That's off. And the last one, you want to have a value of 1 when they're all on, when they're all 1s. The chip enable is on. B is 1. And A is 1. One, 1, 1 here, you'll have a value of 1. And this will be 0, that will be 0, that will be 0, off, 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 and this is on. That's what the inside of actually a 2x4 looks like. 4 AND gates already come pre-designed. You can buy that chip, plug it in, and use it. Only one of these guys will be on. I can make them the reverse, by the way. They're all on except one is low, and that's common too. So you'll see some of them where all of them on and one is low, or all of them off and one is on. All zeros and only one of them at any given time will be 1. You will never have 2 of them on at any given time. Never. The way they're designed, if they're designed correctly, only one of these guys will be on, the way it is right now. The rest will be 0. You can't have 2 of them on. So a 3x8, actually, one will have 8 of these inside them. And 4 inputs. The chip enable, A, B, and C. So we have them 2x4, 3x8, 4x16s. What's a truth table for 3x8 looks like? Let's look at a 3x8 and see what it looks like. I like that paper. So a 3x8 decoder . 3x8. It has 3 inputs from the name, 3 inputs, and how many outputs? 8 outputs. Now I have a habit of writing the most significant one on the bottom. So A, B, and C. A is the most. I have a chip enable that will turn that chip on and off. Again, that could be more than one switch. It could be 2 pins or 3 pins. But for now, for the sake of discussion, we'll say enable is 1. I'll show you actually a picture in our book. This will have how many outputs? 8? 1, 2, 3, 4, 5, 6, 7, 8. Output 0, output 1, output 2, output 3, 4, 5, 6, and output 7. There are 8 outputs on that one. If you were to make the truth table for that, here we go, the enable. I'm going to assume it's 1 for all of them. Then you have 3 inputs, A, B, and C. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Your output, there are 7 of them. Output 0, output 1, 2, 3, 4, 5, 6, 7. What What is 000 equivalent to in decimal? 0. So the 0, 1 is on, the rest of them are off. What's 001? 1. 1 is on, the rest of them off. What is 010? 2, right? 2 is on, the rest of them off. 011, 3. Pin 3 is on, the rest of them off. 100, output 4 is on, the rest of them off. 101, 5. 110, 6. And 111 is 7. If the chip enable is 0, it doesn't matter what A, B, and C are. Nothing is going to happen. Everything is off. It doesn't work. So when your chip enable is actually 1, it does work. Notice some of these chips require multiple enable. Let me look at, in the back of the book, 3x8 is 74, 138. Where is, let's see if I have that. 74, 138. Is that in the back of the book? You have the chip number? Where are the chip number? Here we go, 74, 138. Let's see if we can find that.
It's on page 262.
Page what?
262.
262. I'm just looking for the chip configuration here, the chips that we have.
It's decoders, yeah.
74, 151, 147,
On the right side.
138. See it right here. Notice this chip, particular chip, they're all going to be high except, see the complement, see that little slash over them? Can you see it? Right here? There's a slash over each one of them. I'll put it there just in case you can't see it. It says, for that chip to work, you need to be on pin number 8 to be grounded, 0. Pin number 16 to be what? 5 volts. In addition to that, for it to work, you need pin number 4, that's to enable it, to be ground. Pin number 5, that's the second enable, to be grounded. And pin number 6 to be 5 volts. It doesn't say slash on it. There's 3 chip enable for that. So for this to be on, this better be 5 volts, this better be 0, and this better be 0. Now where this chip works, if A, B, and C, they're all zeros, pin 15, which is Y0, will be low, the rest of them will be high. That complement tells you it's going to be low. By the way, when we draw them, you'll see a bubble at the end of the line. That means we'll be low instead of high. Notice the one I drew here, there is no bubble here. If I put a bubble at the end of each one, that says this pin will be low, the rest of them will be high. When you have 0, 1, 0 or 0, 1 here, this will be low, the rest of them will be high if I put the bubbles here. It's called active high, active low. So this chip, the 131 actually, one of these will be low, the rest of them will be high at any given time. So if I was to graph the 74, 138 for you, schematic for it, I'll do that actually, so you get to see it. Again, the chip looks like this. Oh, I didn't mean to make it that big. Save some room actually here, I'm going to need it. I'll show you shortly how we use them. I didn't tell you how we use them yet. But this is a 74-138. It's a 3x8 decoder. It's actually a negative one, or a low value. 74-138. That's the chip number. Again, our book, it has 16 pins. Pin 1, 2, 3, 4, 5. I'm out of space here. 6 and 7. Okay. 1, 2, 3, 4, 5, 6, 7, 8. It says this is pin 1, it's input A. Pin 2, input B. 3, input C. Pin number 4, it says enable 3, and it has to be a low, which means you attach that to ground if you want it to work. Pin number 5, it says enable 2, and it has to be low. That's also ground. Pin number 6, it has enable 1, and it doesn't say ground. That means plus 5 volts. And pin number 8 is ground, GND, and that you attach to the ground. So for that chip to work, you need 0500 here. Pin number 16 here, that has to be 5 volts. Pin number 15, this is Y0 but has a bar on it. Pin number 14, Y1 with the bar. Pin number 13, Y2 with the bar. Y3 with the bar. Y4 with the bar. Y5 with the bar. And Y6, oh, that's what, 10. Y6 with the bar. There's one pin that's missing.
7.
Pin number 7. 7 is right here. You know what 7 is attached to? Y7 with the bar. Pin number 7. So you have to know where the pins are. 1, 2, 3, 4, 5, 6. I forgot the 7, 7 and 8. And when I graph this, if I was doing this in the lab, I would graph this one actually like this, 3x8. Because I'm not going to give you the pin numbers. I said go to the lab to make sure instead of bar here, I go this one actually works, gives you a value of 0. For 1, the rest will be high. I go 3 inputs, 3x8, A, B, and C. It has a chip enable here. And that enable could be work like you need a low value or a high value. You can see right there. And you have 8 outputs. But because the only one of them is low, you see the bubble here. That's 0, 1, 2, 3, 4, 5, 6, 7. It says only one of them is going to be low. That bubble tells you it's going to be low. That's how you know if it's low or high. So one of these is going to be low at any given time. The rest of them will be high. So if I have to give you the truth table for it, for that chip, I have enable 1, enable 2, enable 3. I better make sure enable 1 is always 5, that's 1. Make sure enable 2, that's 0, enable 3 is 0. I gotta make sure that's these guys on for it to work. Otherwise, don't waste your time and my time. It's not gonna work. You have 3 inputs, A, B, and C. And you have 8 outputs. We'll call them 0, 1, 2, 3, 4, 5, 6, and 7. These are your output. Only one of them is going to be low. The rest will be high. So in this case, this will be low, and all of them will be high. That's how that one works. 0, 0, 1, that's 1. Only pin 1 is low. The rest of them are high. One, 0, 1. 2, pin 2 is low. The rest of them high. 0, 1, 1, that's a 3. Pin 3 is low. The rest of them high. 1, 0, 0, that's a 4. Pin 4 is low, the rest of them high. 1, 0, 1 is 5. Pin 5 is low. 1, 1, 0 is 6. And 1, 1, 1, that's 7. Pin 7 is actually low. If any of these guys are changed, if you put a 0 or a 1 here, if you change that, the enable, it doesn't matter what you put there. If one of them changes, this is off and everything is going to be high in this case. You know, in the lab, we always limit it to what we have for supplies. So this is, which number? 74138. 3 by 8 decoder. Here's the scenario for you. We go into the lab, and I need you to grab a 3 by 8 decoder. So we need 3 by 8 decoder. And I look through all the supplies I have, and I don't have anything. I don't have a 3 by 8. But what I have lots of 2 by 4 decoders, tons of them. With an S, tons of them. And your job is now to take these 2 by 4 decoders and make a 3 by 8 decoder for me. How do you make a 3 by 8 using 2 by 4? So here is what you want. You want a 3 by 8 decoder. I'll make it bigger. So you have three inputs, A, B, and C. And you have your chip enable. And you have 8 outputs. Output 0, 1, 2, 3, 4, 5, 6, 7. And your chip enable high, for example, has a high voltage. When you put 5 volts on it, I want it to be on. You have 3 inputs, 8 outputs. This is 5 volts. I'm attaching that to 5 volts. Again, I don't have that 3 by 8 decoder. This is 3 by 8. So what do I do then? How about if I take a 2 by 4 and put it right there? Two by 4 decoder. That'll give me 4 outputs. Has 2 inputs. And I get another 2 by 4 and put it right there. This is a 2 by 4 decoder. Normally a 3 by 8, when I put 0, 0, 0, this one is on. 0, 0, 1, this one is on. 0, 1, 0, this one is on. 0, 1, 1, this one is on. So when A is 0, this one is on. When A is 1, this one is on. These outputs right there. Because once I put 1, 0, 0, pin 4 is on. 1, 0, 1, pin 5. 1, 1, 0, 6, 1, 1, 1, 7. So when A is 1, I get the bottom 4. When A is 0, I get the top 4. I got to make sure it still works that way. Here's my chip enable. I can attach B and C to this, and B and C to this. When B and C are 0, 0, this one is on and this one is on. But I want to limit that. I want it based on A. So what I could do, I can actually have A drive my chip enable. I can put a NOT gate when A is 0, enable that. When A is 1, go to this one. If I want to use a NOT gate. If they don't want me to use a NOT gate, use only 2 by 4 decoders, no problem. I'll pick another 2 by 4 decoder. Actually, I'll do this, different color. I don't know why I made it that big. Take another 2 by 4 decoder. And I'll attach this to 5 volts immediately. So this is always on. That's enable. Well, it has 2 inputs. It has 4 outputs. I'm using B and C here. If I use this for A and use this to ground, that's one option. If I make this ground and this is A, when A is 0, 0 and 0, which one's on? First one. So that's my chip enable. When it's 1, 0, 1, which one is on? Isn't it the second one? That's also my chip enable for the bottom one. So if I don't want to use a NOT gate, if it says you can't use a NOT gate, you have to use only 2x4s, I can set it up this way. And now by using these, I got my 2 or 3x8 decoder using only 2x4. So if it says only 2x4, you can't use a NOT gate, you got to use a decoder. If I want 4x16, perfect. I'll use 4 of them. I'll use this to enable the top 4, the next 4, the next 4, the next 4. This is what a 4x16 decoder looks like. Notice the top 4. We're using the most significant A and B here. C and D go into these. So when C and D is 0, this is low, this is low, this is low, this is low, because of the bubble there. The rest are high. But A and B are going to tell me which one of these is going to be on. When A and B are 0, 0, this guy is low, and that will enable that one. 0, 1, this guy will be on. 1, 0, this guy will be ready. 1, 1, this guy will be ready. So we use A and B here to control this, and these actually will decide which one of these 4 will be on, and that will activate one of these 4 decoders. So how do we use decoders to build a function? Like we've been talking about decoders the whole morning there. How do we use them? So here's an example. Let me give you a function. F, A, B, and C. I'll do a 3x8. Equals the summation 1, 2, 4, and 6. Another one, G, A, B, and C. The summation of them in terms of 0, 1, 5, that's good. And I want to design both of these functions. Simplification is not my concern. I don't care about simplifying this or not. When we start using these devices on the market, I don't have to worry about that. Let me simplify it. Doesn't matter. So I can grab, since that's 3 inputs, I can grab 3x8 decoder from the closet. It has 3 inputs, A, B, C. My chip enable, again, if it says bubble here, if you see a circle like this, that means you need to put a 0 voltage here. That's your enable. If you don't see the bubble, you need to put a 5 volts to enable it. So I decided to switch this one, make it a 0. And I have 8 outputs coming out of this. Pin 0, 1, 2, 3, 4, 5, 6, 7. That's 3 by 8 decoder. To design both of these functions, you only need one decoder. You can do 10 of them, 10 output function with one decoder. It says, I want it to be 1 for F when you have 1, 2, 4, and 6. All you need is an OR gate. And which pin you're going to attach to it. Number 1. Number 1. Number 2. Number 4. And the last one is what? Number 6? That's the F function. F will be 1 when 1 is high, 2 is high, 4 is high, or 6 is high. What's G? Another OR. And when 0, 1, and 5. So here we go. This is the 1. And this is the 0. We'll do the 3 of them. Bless you. I'm just going to run them through. You only connect it if you see a dot like that. So it's not really connected anywhere. That's the 1. And we say what, the 5? If I jumped over these, we'll look a little bit messy there. That's why I don't want to put the jump over them. So the 1 is attached here, this one here, and the 5. That's it. So this is 0, 1, and 5 going to this. To this one is pin 1, 2, 4, and 6. And if you have a third one, you attach the pin. Just take wires from these holes there and attach them, and there's your circuit. Do I need the K-map to simplify? No. Do I need the Quinn-McCluskey to simplify? No. Do we simplify? No. The problem with this, when you have a lot of these, your OR gate's massive. So if you have like a 4 by 6, a 4 input function there, that's where it becomes a little bit ugly there. And by the way, if you have a don't care, we don't even connect them, because you don't care if the value is 0 or 1. Why make life complicated? So let's say we have this. One, 2, 5, 7, 9, 11, and 15. Don't care. At 3, 4, and 8. That is a 4 variable function. That means I need 4 by 16 decoder. Bigger one. You get 4 inputs. A, B, C, and D. You get your chip enable. And you get 16 outputs. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So your function is going to be an OR gate, so it's a big OR gate. There are a lot of pins going to it. And which one are you going to attach to? I'm not going to run the wires, it gets really messy. I'll take the wire from pin 1, pin 2, 5, 7, 9, 11, and 15. So you take all these wires from here, you attach them to that OR gate. And that's it. What about the don't care? We don't care if it's one or not. Why even bother attaching them? So you're just going to have all these wires from here to there. 2 to 2, 5 to 5, 7 to 7, 9 to 9, 11 to 11, 15 to 15. So if I attach them there, it will look a little bit ugly, if it's a straight line like this. 11 to 11, 9 to 9, 7 to 7, 5 to 5, 2 to 2, and 1 to 1. You grab these wires and you attach them to your OR gate, and you get your function. We use them all the time. No need to simplify, nothing. And again, you could have multiple function. I can have another function, H, A, B, C, D, and just different one, just take the other pins, whatever you need, and attach it to that one. So that's what a decoder is.